I wanted to talk about how we use mathematics to understand viral infections, but actually I want to tell you today how we use insights into viruses to understand packings. And this comes from discussions I had with a couple of people. Rosie is there, Michael is there. So I hope I can show you that actually via studying viruses, you can get these dense packings in a different way. So no further ado, Farzad already has introduced very nicely those tiling problems that we are looking at in this team. This, it doesn't need much more introduction. Suffices to say that we're looking at viruses from the point of view of their surface structures and trying to find these roadmaps that explain to us the positions of the proteins. But if we look at Caspar-Klug theory, there are two mathematical problems arising that we've been looking at in our team over the years. And these are that these surface lattices that Caspar and Klug use are too restrictive to understand the plethora of viral structures that we know exist in nature. And there's just one example here on the left-hand side that inspired a paper we did in Nature Comms in 2019. The other thing is this arrangement here, which is reminding us of quasi-crystalline arrangements, because the proteins are coming together in groups of 5 here. So there are 72 pentamers, very much related to what Farzad talked about. And that is the structure we need to look a little bit deeper into today in order to glean information about packing problems. So here, one last slide about the tilings. I wanted to give a summary. Farzad has done a fantastic job, and I want to advertise his work in general. He's done really amazing work in the team. So the problems that Farzad has looked at, as he explained to you, coming from the Caspar-Klug situations where triangulations are sufficient to explain many viral structures, and going to the connectivity between them and understanding basically how they interact. He explained to you that we need these different surface lattices, and that's actually the virus I mentioned to Greg at the end of his talk. So this is the one that actually uses frustration. We can talk a bit more about that. But then we are coming to the point of these other surface connectivities. These are the dimer and trimer interactions. We suddenly have protein units that do no longer interact in the same way with other protein units, but there is one of two possibilities, namely this dimer interaction between pairs of proteins and trimer interactions between triplets of proteins. And the big conundrum we've been faced with, and where Farzad made a really important contribution, is to understand what happens when suddenly some protein units do not interact at all, while others do. Because a tiling, to be mathematically and biologically meaningful, should have units that can be directly interpreted in terms of biology. But if you think about what we're doing here, either we use interactions or we use proteins, but neither works here, because if you use proteins, you see you have the big gaps. How do you represent a gap in the tiling? Then if you think about interactions, there are some proteins that do not interact. So again, we have gaps in the interaction network. And this is the mathematics that Farzad spoke about earlier. But what I would like to do is invite you a little bit on a journey on where these two-dimensional tilings actually come from, how they sit in 3 dimensions, and how they relate to wood structures, because that is the key to understanding packing problems in this situation. So this is, again, this one of the two problems that I highlighted at the beginning, where we have these old pentamer capsids. And if you look at them, they're very reminiscent of the first face value of Penrose tilings, because what you see here, you have these local 5-fold interactions. You have vertices where you have an arrangement of 5 tiles around them, but we only have one vertex of global symmetry at most. There are no other 5-fold axes that can be global in this situation. And here we see the diffraction pattern that led to the discovery of these quasi-crystals. Now, in order to understand this from a mathematical point of view, I have to introduce a little bit how we model this. So there are different ways of looking at this, but for me, coming from lattices, the way I see this, I'm given a symmetry group of interest, in this case, say 5-fold or 10-fold symmetry, and I need to find a lattice structure where this is crystallographic. So in other words, if I want to write down a representation in terms of matrices, I want those matrices to have integer entries. One way of looking at it. And what you can then do, if you have that lattice, you can look at, if you get to think in terms of matrix representation, you look at invariant subspaces. And in this case, what you do, you make a basis transformation. So you have a two-dimensional invariant subspace where your structure lives. And then in this case, you have a complementary space that's three-dimensional. We call it a control space. And we are admitting certain portions of the control space to deliver vertices in my model space. Now, the same thing can be applied to icosahedral symmetry. We just, in this case, use a fixed dimensional lattice up here to create in a three-dimensional model space tilings that are now three-dimensional. So we have these two shapes here that make up this generalized Penrose tilings, if you wish. And then we have our control space again. Now, what's really important if we want to classify packings eventually, we need to understand what is the spectrum of possibilities from a mathematical point of view that we've got here. So what I'm asking really is which lattices in 6 dimensions support icosahedral symmetry. And indeed, there is a classification that tells me these are simple cubic, face-centered cubic, and body-centered cubic lattices. And this will become important later when we're talking about packings. Now, how does this solution here then sit with what I've told you about three-dimensional Penrose tilings? Well, you can view those tilings that Farhad nicely introduced to you as spherical sections in a three-dimensional structure. So here's an example. You have a virus that is embedded into a three-dimensional tiling. You see it provides encasing forms. There's beautiful work by someone called Jana who did encasing forms with lattices. We've done it with quasi-lattices. And you can see, or you can contemplate then these tilings as being spherical sections in these basically larger tilings here. So now, what can we learn for packing problems? That's why I'm here, that's why I've been invited to come here. So let's see what we can do. Now, in order to understand this, we need to now ask the question, what is actually the mathematical structure from a group theoretical point of view that's lurking underneath these tilings? Now, if you look at the hexagonal lattice here, or you can also think of it as a triangulation if you wish, then there is a mathematical concept that's called an affinization. So we have a symmetry group that is, say, a rotational symmetry that is going around a 6-fold axis here. And now I need to transport that structure in space. So I'm introducing a translation. But I'm not doing this just in any possible way, because then I have no mathematically meaningful structure. I have, of course, to do it such that when I translate the original structure, I have coincident vertices here where they glue together. So this is the idea of a periodic tiling here, and Katsumudi's theory is basically the mathematical framework that would tell you how to do this. But now we have a problem, because if we are thinking about the simplest analog that's non-crystallographic, so a pentagon, what do we actually do? Because we have already got results that tell us we can't just glue it without gaps to other pentagons. But from a mathematical point of view, what you really want are non-trivial group relations. So you want that there are these rotation operations, translation operations that are such that the translation is chosen such that you have identities that make the group non-trivial. It's not a free group. It's a non-trivial mathematical identity. So geometrically, what this means for us, we need to determine translations which are such that when I then subsequently use the rotations from my symmetry group, again have these coincident vertices, as we call them. So here they are trivial via a movement of that shape. I have these two coincident vertices, but here I generate them such that when I rotate, I create these vertices, they coincide again. So the question, therefore, is from a geometrical point of view, what are all the ways to get these coincident vertices in such a setting? So here is, we're going a little step further. So what you see as the decagon, and we see more about it on the next slide, is actually an embodiment of the root system of a non-crystallographic Coxeter group. So Coxeter groups are reflection groups, and they are determined by the vectors perpendicular to the reflection planes. Here, if you take a vector from the center to this vertex or to that vertex there, then they give you two reflection planes and the others are sort of implied by it. That's why these are sort of the simple roots, as we call them, that define the group structure. So now you can, from a geometric point of view, do exactly the same thing again. You can ask the question, what are meaningful translations so that I get these coincident vertices? And you see that playing out here. So this is obviously one that's been chosen, such that when you then rotate, you have these vertices being reinforced through the copies that come from rotation. And what's more, when you do this, you will notice that you will always end up with a vertex, and that's why I've got the Penrose tiling for you in the background, on a vertex of this original Penrose tiling. So now you can do this over and over again. So we have fixed the translation, we have fixed the rotation. All my choices have been made. So now I can translate, rotate again, so I can actually iterate that process. What happens? So the next iteration would create the red vertices. Notice that they again on vertices after Penrose tiling. This is not accidental. That has to do with the number theoretical properties. Again, a little bit is on the next slide on that. But I first wanted to provide intuition for what we're doing before I'm throwing some formulas at you. Yes, so basically you get this intuition of gradually building up. So you're building outwards with your point array and you're making it finer, but you are guaranteed to sit on the vertices of such a Penrose tiling. Okay, so here's a little bit of formulas. I'm sorry about that. So basically, this is my root system expressed in terms of an extended number field. Tau is an irrational number, and A and B are integers. So what you're doing, basically, you have these two roots, simple roots alpha 1, alpha 2, and the other roots are now Tau linear or Z-Tau linear combinations. So this is where I'm giving up from classical Kac-Moody algebra, the integer set. I use an extended integer set, and you can understand it comes from those projection directions. We can go into this, ask me if you want to know more later. But formulae, it's a very simple thing to do. So you take your Cartan matrix. So sorry, I haven't introduced that. Cartan matrices are placeholders for the relative orientations of the angles. So they contain the scalar product between the vectors normalized. Should have introduced that properly. And this is sort of an extension by adding a row and a column. And if I want to generate this infinite set, the determinant has to be 0. It's really Kac-Moody theory with a different number field that we're doing here. And so if you do this in this case, you get an affine reflection that is transporting you in space. Right, so here is a little movie, and I think I have to start them from here each time, but that's perfectly fine right here.
No, on the main
the main one, sorry, yeah, thank you. A moment, coming here, coming up. So these are little movies to show you how this works. So this is, again, a summary, a bit of what I've just been talking you through. So it should bring this root system in and show you how this works. So just to recap that part before I'm moving to the three-dimensional case. So again, we see here in action this affine extended group. So you see really we have a translation of rotations, and each of those rotations are set up to generate these coincident vertices here. That's really the key in this example. Right. Okay. So now let me talk forward. So now the question is, can we do a classification? So we said, again, coming back to my simplest example, there's a pentagon, I'm moving and I'm rotating. So the question is, eventually I want a full classification because I hope to get packings that are densest. So I should better not miss anything that is possible, because that might be my densest packing that I'm after. So here then is again on the simplest example I can think of, showing you the intuition behind the classification. Obviously here it's rather simple, but it gives you an idea. So you see the symmetry axis of the original pentagon, and if you translate in ways such that the translated copies intersect with the symmetry axes, you are guaranteed that you get the property I've talked about, because if you now do your original rotation, you obviously reinforce, and you see this play out now in this movie, you obviously reinforce the vertices that were hitting the symmetry axis, as you would expect, right? So, and that's the intuition I would like you to take away when we're going in higher dimensions. So the idea is the same, but obviously we are doing this now in a higher dimensional space. And so here is an icosahedron. So now we're doing in 3D. And now I want to translate it so that when I now rotate around the center of the original structure, so I'm rotating around one of its threefold axes, what I'm doing is I'm creating these other copies. And you see, it actually tessellates, but with overlaps at this point, a rescaled version of the icosahedron. I just draw for you one triangular face of a larger icosahedron. So if you just choose your dimensions just right, you can just get this overlap, a filling of that structure. But obviously we are talking about packings where things don't overlap. So we are interested in other packings. So what do we need? Well, so the virus, as we know, uses icosahedrosymmetry. So this is, we can again cast this into a reflection group, and the Coxeter group has obviously double the, there's an inversion as well. The icosahedral group has only the rotational symmetries. But the way to see this again is to think about symmetry planes. So look at the structure down here. What you're seeing here is an icosahedrodecahedron, and you obtain these twofold axes of icosahedrosymmetry by intersecting these planes that are orthogonal to the roots of this Coxeter group. So again, I'm just given a set of vectors. The vectors are perpendicular to planes. Then these planes replace the lines we had on the decagon. Now we have planes, but it's the same idea. And we are having this icosahedrodec that you're actually getting as a polyhedron if you connect these vertices here. And so now let's have a look at how this pans out. So now you can do exactly that same mathematics. So basically you can also relate it to lattices in high dimensions. So this would then be lattices that you might be familiar with if I unfold them for you, like E8. You see or D6 in this case, and you can basically project it in these different subspaces where our irrationality comes in. Talk to me if you want to understand how that works. And you basically get then this root system of this Coxeter group in this model space where we want to model our structure. And this is just to show you how the vectors sit, if you're interested in that. Okay, so now again, you can do that same procedure, which is this analog to Kac-Moody procedure, and extend those carton matrices here. And what you then get are, in this case, these point arrays that come from the translations that we get via this formalism here. So now let's have a look at how this pans out. So I appreciate not everybody here is interested in group theory. So just think about, again, that idea, but now playing out for us on an icosahedrodec. So now we're translating along a 5-foot axis, and then we are rotating again and create this point array in this way. So again, observe how these points are coincident. So this is the idea that we've discussed before. So we get these coincident points and really have a highly constrained system here. And there's only a finite number of these options, as we've seen on the pentagon, just a few more here to do this. And you get these point arrays basically, and you see you end up with this library of point arrays that come from these affine extended groups. They embody a compatible group structure here. Okay, let's see, maybe we should, in the interest of time, you've seen how this works. There are further iterations there. So yes, so in the interest of time, I'm moving forward in a minute here. Just give you a little bit more of an insight of how they work on viruses. Yeah, but here we are talking about the mathematics. So as soon as you've seen the point array, I'll move forward for you. Yeah, so just to give you a feeling for what these structures are. Okay, so now the next question we have to ask, what are meaningful start configurations? So what you've seen is we have started with an icosahedrally symmetric structure, and then we can geometrically answer our question. But it will depend on the choice of polyhedron you're looking at. And the question is, which polyhedra are actually relevant? And that can be answered by the lattice theory in the high dimensional space again. We know that there are only 3 lattices in 6D that have icosahedral symmetry: simple cubic, face-centered cubic, body-centered cubic. Now project the lattice basis into the 3-dimensional model space, and what you are getting is a shadow, which is an icosahedron, an icosahedron or a dodecahedron in this case. And that's relevant because that's what we need to look at. So here are just some examples of viruses. I appreciate this talk has an uncharacteristic level of low virus density for my talks recently, but at least a few should come in. So you see how different lattice types would pan out. So the BCC lattice would kind of provide models like this, face-centered cubic lattice, which is the icosahedron like this. So again, to not quite lose completely this virus aspect in this talk. But again, we want to learn from viruses, not for viruses today here in this. So let's go to the point arrays. This is actually animated to show you a bit how it looks. So we have a library then of these configurations that we call a library of point sets that are embodiments of these symmetry, an extended symmetries that we've been discussing here. So now just a few slides about how we use it before we go to the packings. So you saw already this tiling in Fazat's talk. Now, when you embed this in this larger framework, you get additional information about structure. So here's one of those pentamers from the side. So the one that sits around the 5-foot axis is shown from the side where it has some thickness to it. And you can see that these vertices that correspond to this model actually quite nicely delimit its dimensions. Is again the idea of encasing forms that Jana introduced. Then here we see a virus that is basically having this appropriate point array overlaid. And when that was actually the first one we worked on at that time, and you see that the density of RNA actually is very nicely fitting with the organization overall of the virus. And who was at my talk on Monday has seen how we had the whole industry over years using that mathematics to learn information on those binding sites between the RNA and the protein from that, which we can cast into these polyhedral shapes that show me connectivity between these binding sites. And we've used those ideas of Hamiltonian paths between those binding sites to introduce a new data analysis method that enabled us to identify packaging in 2 minutes. Only up we get there. Thank you. Identify packaging sites in viruses. So actually, at that point, we have exploited the fact that viruses learn about the traveling salesman problem. So they tell us something about how to solve a traveling salesman problem. Ask me about this in my talk on Monday. So I'm not saying more. Talk to me in the break if you want to know this aspect. I also want to say that this upper and extended mathematics tells us something about nested shells, like nested carbon cage structures, carbon onions, and we've shown that the same mathematics also applies to these. So it's a fundamental mathematical concept that was developed for viruses, but actually turns out to tell us a lot more. We can even have it in 7-fold symmetry, really quick this. Probably just show the beginning of that. So again, you can do this for other types of dihedral symmetries or other types of symmetries. So this is a very general concept, and we've indeed applied it to other protein structures. It's a Gruyère. It's very universal in biology to use this. So, but let us move forward here. The problem allows me. So what I've shown you so far is that we know about icosahedral symmetry in viruses. We have talked about the surface tilings, and we've seen in this talk that they actually arise from sometimes packings with overlaps, but clearly also there are these packings that are non-overlapping. And we have these vertices, which give these point arrays that are basically the vertices belonging to the corners of those shapes that we've been packing into icosahedrally symmetric larger shapes. But now comes finally the punchline. So what we then can do, we can ask, we have a classification of all these upper and extended symmetry groups. We can filter for those which do not lead to overlapping packings, but packings that basically are such that either faces touch, vertices touch, edges touch. We had this in a talk earlier in the week. So we went ahead and we computed the packing densities for different arrangements. And I'm not showing you all of them. I just show you a couple that are relevant to the discussions we've had here. So basically for the icosahedrodecahedron, the FCC projection, this is the densest packing we found, 0.864720. We have another packing in, but that's not quite as good. And we have see here also not so good packings. But what was really nice, please watch that number, because after talking to Rosie and Michael, that's from their papers. I want to advertise a paper that they made me aware of in this conference, which I didn't know about before the conference. So this conference really does the job here. So you see here, we saw in Rosie's talk already a similar argument for a different type of symmetry, but this is now the same for icosahedral symmetry. So you see different incarnations. You see the icosahedrodec here, you see the icosahedron here, and the dodecahedron here. This is their way of representing how they behave by way of packing. So the things that behave similarly are classed in an area, and you can see there's a similar behavior here, but quite a different behavior here. But I filtered out this table from their paper where they give me those packing densities, actually numeric and analytic, and look at the one that we found and look at their values. So that's actually quite nice, because it means that the affine extended groups really hit on the densest packing for the icosahedrodec, and so we have an orthogonal view in some way on the packing problems that you discussed with us from that point of view of these lattices or quasi-lattices and these affine extended groups. So is this a small summary here? So wire tiling theory tells us a lot about icosahedral structures in general, as we've seen here, but mostly in the team, as Farzad said, we're using this in combination with other techniques to learn something about mechanisms and viruses. And we made a number of discoveries together with other teams, experimental teams in our team, many people involved in our team in a mechanism how viruses work. And in particular, in this talk, I've shown you how these affine extended groups can also tell us something about polyhedral packing, which we're interested in this community here. So here are my thanks to the team, many alumni also involved in the early stages of those developments, our experimental collaborators who have joined grant funding here, and in particular Farzad, who's doing stellar work, and he's talked to Farzad. He's the mentor for all these wonderful tiling problems. Yeah, and with this, happy to take questions. Thank you.
So we have time for a couple of questions. We have one full cancelling afternoon, so we can put everything in. You will get your half an hour break, and you will come in at 11:45. So we have some time for questions.
Thank you.
Thank you for this very visual presentation, how you generate quasi crystals. That's the first time I've seen that. I was wondering, still, forgive my ignorance, I understand space groups, I understand how they're made out of translations and rotations. How is that with Coxeter group? What are the elements of
Oh, very, very good question. So the elements of a Coxeter group are reflections. So basically reflections generate rotations. So we have basically icosahedral symmetry has the 60 elements that are rotations, 5-fold, 3-fold, and 2-fold rotations, but you can generate them via those reflection planes that we've had in one of the slides. So we go back to the slide real quick. So it's really reflections at those planes. So the planes that intersect here, these planes are the elements of the group, are these reflections, but you don't need all of them, because some of them generate the others. So that's what we call the simple roots are for us the vectors perpendicular to those reflections that you need to generate all other reflections.
So they're just mirror planes.
These are mirror planes at this point. So what do I do with an affine extension? I create a mirror plane that's off center. But if I take anything, I get accumulation points, I get the free group, I get no structure. So the whole business here is about taking translated planes that have a meaningful distance in the sense that, and that is dependent on this, what we call start configuration on these polyhedra. So fix your polyhedron of choice. Then I put the dodec. Now I'm asking the question, I want an off-center plane such that when I translate and rotate, I'm not creating as many vertices as you would get if they wouldn't coincide. I want some sort of coinciding vertices. And the way to construct this mathematically is to think about the symmetry of the rotational group of the original group. So you have 5-fold, 3-fold, 2-fold axis. So imagine you're transporting yourself so that your vertices intersect with these planes, and then you do your rotations, you reinforce those vertices. That's the anti-intuition here, but you can get this mathematical machinery. So this is obviously a way of thinking about, because I always like to think about it in geometry and in space, but then you want to transformalize, and then it has to go to the Coxeter roots. And what's really helpful is these root systems, because they know it also. The roots basically are the vectors perpendicular to those planes that are sufficient to generate all the other actions of the other planes. Yeah. So here you see for every element of the Coxeter group, you see a plane. There are many lots of planes, but you know that if I use 2 or 3 in order, I have the same net result as one of the ones that's already in the group, right? So that's why when I work with this, I'm only thinking about the simple roots, which are the characteristic basis planes, if you want.
Like the generators of
the generators are reflections. These are reflections. You can write them down as x alpha is equal to, I mean, just x minus 2 alpha x over normalized, right? So it's really like when I compute with them, I compute formulaic with them, right? So basically I use them as reflections. Just reflection. What's really interesting, and I think we had a chat with Greg also about hyperbolic geometries. So these are obviously Euclidean, because if you take the determinant of the matrix, it's positive. But you could also have, you know, a setting where it's negative. And then you can do the same thing. So you can forget about, in a sense, the geometric insight I've used to communicate the ideas, and to say just go back to the Cartan matrix, go back to the formulas, and just work. That's the thing I mentioned. You could just go and work with those, and then just carry it through on paper. But the idea is sort of that same one. Yeah. Oh yeah. Yeah.
Can I ask a somewhat naive question?
Any question?
So here we're working with a fairly symmetric object.
Yes.
How does this procedure break down once we work with less and less symmetric objects?
That is such a good question. So first of all, the start configuration is the symmetry we're using, and the whole idea consists in translating ourselves such that we hit one of its symmetry axes. Now, if you reduce symmetry, you can still do some of that as long as some symmetries are left. But then you're weeding out everything that's not translating such that you're hitting a symmetry axis. So
if I'm working with a really complex molecule that really doesn't have a symmetry axis.
If there's absolutely no symmetry axis, then I don't think that works for you. But as long as any symmetry left, then that can be used to create that same thing. Yeah. But without a symmetry, then that matters not. This will give you the dense packing for something with some sort of symmetry. At least a subset of the symmetry. Yeah. Yeah.
Related.
Yeah.
On then kind of interpretation experiment. So show this example, which I also showed earlier, the extended pentameric unit, and it had these yellow and magenta points that were at a different radius.
Mm-hmm.
And somehow you have to make a choice to say, well, there's part of my protein there that is important.
Excellent question. Where are you going?
Biologists are going to say this is important.
Yeah. So what?
So it actually fits my structure.
That's a super important question. Right. So that was the thesis. The entire thesis of one of my PhD students was just that. So the question is, you have this library of point arrays given, that was Jess, right? And then we are saying, okay, we use the protein layer to make an RMSD fit onto that. So I can talk to you a bit more. So it's about, we were looking at proximity to atomic positions in the protein. So you
residue relative.
Yeah, exactly. And then also so if they occur with symmetry, then the symmetric copies have to be there as well. So it's an RMSD. So she's basically developed an algorithm for that. And then the miracle for us was when we applied it to viruses, we said it's the gauge shell, we gauged it on the protein layer, but anything that was a statement about the packaged genomic material was a prediction. And it matched really nicely. I've got a movie that's on my computer, it's not here, where you see how it really matches in the minor groups of the molecule. I mean, it's an amazing fit. There was a little bit of that in one of my images, I think. I had I'm sure you'll find it so quick. The one with the MS2, right, where you see, do I have it here? I hope I have it. Here, good. Yeah, so basically, you see the outside is the protein container. So that is the only part that's been used to find the correctly matching element from the library. Anything that's inside is a prediction. And now you're switching the RNA on and you see how it sits. So that has not been used to identify the model, because you're quite right. You can fit almost everything, although I should say the library is not that big. So there are on the order of 40 structures in some way, because you weed very quickly, you weed structures out if they have the wrong base structure that's being translated. So there's only a subset that's relevant anyway. But you're right, you could then ask the question, do we overfit? But all of this inside here is a prediction and it sits very well. And this is not an insular case. So very different families of viruses, very different structures. We find that same sort of level of fit on the inside. And that's the moment where we realized there was some meaning to those structures. And then we used it in so many other applications that obviously I didn't have time to touch. But yeah, thank you.
Okay, so thank you very much.
Thank you so much.